let me share the screen with you. But before I do it, I must say that I posted in the chat the slides from this workshop. So each of you can have it as a notes for this workshop. And yesterday as well, I sent you the email with all the code we're going to talk about. And you can use this code for whatever purposes you would like, but you can use this code as well. And this is my request to you for practicing the statistical analysis in R. Um, I'm, yeah, let me share the screen. Do you see my presentation? Okay, perfect. I'm going to talk about the statistical analysis of eye tracking data in R. R is a computational language, but the slides are written in R actually, but I'm going to try to translate it into English. So you can just sit, relax, and listen, or you can try to do what is on the slides and what is in the code I sent you yesterday by yourself during the talk, whatever you like. I'm happy to take any question whenever it comes to your mind. So don't hesitate to ask the question and on the chat or just interrupt me and ask the question. This is meant to be a workshop, so I'm not stick to slide presentation. We can extend it with your questions a lot. So talking about the statistical analysis or analysis of the eye tracking data, we may think of it as a at least two-stage process, because the first process, the first stage is to obtain the relevant matrices from the eye tracking raw data. And this stage, I'm not going to talk about. Andrew Duchowski, who's going to have the workshop after the lunch break, we're going to talk about this stage, how to obtain the meaningful matrices from eye tracking data, starting from getting fixations and saccades, at least. You may use a various of softwares for that, or you may use your own scripts, and probably Andrew will talk about it much more. I'm going to focus on this second stage when we have already the data with the matrices, at least with fixations and saccades. With the real eye, about which platform we were talking about yesterday, it's super easy to obtain these matrices and download from their platform just after finishing the study. And if you have these data, you can perform the analysis, such analysis which are tied to your research question and hypothesis. So the agenda for this talk is to introduce you with the R language. Those of you who don't know R yet, and RStudio as the interactive development environment for R, which is excellent development and used very widely. Why R language? R is a statistical language developed by statisticians, for statisticians, and for those who are using statistics. And it seems to be a gold standard now when we're talking about the statistical analysis. So the basics will be covered here. Then we'll move to basic descriptive statistics, which are always needed. And then we'll move to the moderation analysis. And I'm going to talk about two types of moderation analysis. And one type we're going to use well-known ANOVAs, especially mixed design analysis of variances. Isa talked a lot about the mixed design, and we'll try to feed the statistics to such a design. And of course, when we talk about the mixed design analysis of variance, and when we talk about the moderation, we cannot talk about the interaction effects. So we'll have ANOVAs with interaction effects, and follow the interaction effects. We'll talk about the pairwise comparisons, sometimes known as well as post hoc analysis, and we will end up with graphical representations of effects, of significant effects. I'm going to show you uh, how to produce publication-ready graphs with your statistics for your papers. The second analytical method mm, of moderation we're going to talk about is regression, and it's going to be a bit more complicated with multiple regression with interaction effect, widely used as well, and which is often followed by simple slopes, sometimes called trends analysis, and of course visualization at the end. This second point, this is the second type of analysis is getting more and more attention of researchers, and it's going to be an, I guess, some kind of an introduction to tomorrow's workshops or lecture given by Agnieszka and Breno about linear mixed models, which are super advanced in modern type of analysis. So I'm going to leave this advanced stuff to them and focus on something more basic, like me. So R and RStudio basics. I already introduced R. If you somehow experience in R, please forgive me if I'm doing something in R differently than you, because R is a computational language, so it gives you a lot of flexibility of how you achieve your goal, how you do the analysis, how you perform ANOVA regression. There are several ways to do it. I'm going to talk about the way I'm used to do. I'm used to use. I'm a simple psychologist, so I use the way I think is the simplest for social scientists. Uh, yeah, let's move forward. Or you can download freely from rproject.org website. This is the collaborative open source project, extremely popular right now. This popularity is super useful as well for us as users. It's not only fancy to say in a paper that we did that analysis in R, it's not only that, this is even not important, but this popularity means that there's a huge community of people developing and people using R. So if you're gonna have any questions, and for sure you're gonna have a lot of questions while performing your analysis, you can almost always, or 99%, find an answer on on internet because people share the code, people share experience, and share the way how they approach the analysis, how they do it. I often use Google when I do my analysis. And the RStudio is really great tool for writing code in our running the code and seeing the statistics and graphs. It's super useful with a lot of help embedded, and it's also free. There are some paid versions of RStudio, but for 99.9% of us, the free version is just more than enough. So these two things, it's good to have on your computer. First, you install R as a language, and then you install RStudio. And if you have it installed and you run RStudio, it opens R automatically within RStudio. So there's only one software we're going to work with. This is RStudio. And all the examples I'm going to show you are done in RStudio. So a couple of slides for introduction to RStudio environment. When we just starting working on a new project, it's good to think about it as a project. And it's good to keep order on your computer especially when you do statistics. It's not the easiest thing to do in life, but keeping order is important. So uh, think about the folder in which you're gonna store all the statistics, data, and graphs. And even you can make such an order on your desktop within your in your documents folder. Um, Name it somehow you like my my new project, my new fantastic project, any name you want. So how we start a new project in RStudio, we choose from file, new project. I'm using Mac if you, as you can see, but the interface looks super similar in any other operating system. And RStudio is working as well on super well on Windows machines and on Linux machines, whatever you like. So we start from file, new project, then in the second step, there's this prompt window asking us what we want to do. Uh, I can choose a new directory because I have not created the directory yet. For the directory means the folder. I have not created the folder yet. I want R to create this folder for me. So I choose the new directory here. And in the third step, I choose the new project, which I want to do. And in the final step, it asks me for the name of the project and where I want to store it on my home computer. Um, as you can see on the slide, uh, step 4, I will create a leadme directory, leadme folder on my desktop, right? And then I click create project and I have it. Now it's good to go outside the R um, and open your folder browser, whatever you use, like a Windows Explorer uh, or Finder on Mac, whatever you have there. And a good advice to keep in order is to put there in this working directory. We'll call this your project folder working directory. Okay, that's the name I'm going to use, working directory. Put in your working directory the data. I keep the data in a subfolder, as you may see here, and I create as well empty folder called graphs. I'm going to keep the statistical graphs there just for keeping in order and keeping everything clean. So let's go back to, if I do it, I go back to RStudio, and the RStudio ready for use should look like this. It is somehow combination of 4 windows. At the very first step, you will see 3 windows only. You will see R console, in which you run all the statistics and in which all the statistical results are going to be displayed. You see, uh, you see the huge window with different tabs, which is basically our environment. Our environment is like a working memory of current session of R. So this is like our desktop. You have a history here, connections, tutorial. We're going to use only our environment. So anything we're going to do, any object we're going to do, data we're going to load into R are going to be visible here in this R environment window. And we have more complicated window with 5 tabs. Um, these are files, and automatically when you create our project, you see you see your folder, your working directory with leadme rproj file. It's for opening the project later on, for example, tomorrow. You have a tab with plots. If we're gonna produce any plots, they're gonna be displayed here in this tab. We have a tab for packages. We're gonna use it later on. So wait for that, please. And help, which is super useful too. to use all the time. I'm going to talk about these stuffs later on, of course. I have the fourth window here as well. Now, because what I did already, I created R script. And how we can do it. Do you see my marker? It's a pen. I created R script using this button. When you click on this, there's the whole menu and you choose the R script. We're gonna write in this R script all the code, all the analytical code we want to perform. And then we're gonna paste it to the console to execute the code. And this script is gonna be saved forever on your hard drive on your computer. I created a new R script. This is a text file with, I call it analysis, for example, or different name you can choose. It has extension .r, big R. It's computer knows then it is R script. So when you create it, you're gonna see it as well in this files tab here under analysis R. That's my file, and this is my script. Why it's good to have the script? Because anything you paste into console, anything you display on the console will disappear when you close your RStudio. Okay, but no, sometimes we need several hours to work on analysis, and you don't need this. You don't want to see the several hours at once. So you write the script, and you can then close the RStudio and come back to this next day, right? So everything is already written in the script. There's like a history of our analysis. Right, let's check the next slide. And now when we're talking about the R script is written in R language. If I think about this language, this is like this programming language, and this like any programming language, it means the good metaphor is like giving orders to the computer or asking for something. When you think about if you're hungry for lunch and you want to have a pizza, right? So you can think of, let's create an object which is called lunch. And we have the object lunch, and that's our name. We give into this object. We want to have a lunch. Let's create this object, and this sign, the error, this is assignment. It means that the lunch is going to be created by the rest of the code. How you want this lunch to look like. Let's say that you have a taste for pizza. So we will ask computer, hey, make a pizza for me. But the computer doesn't understand English. It does understand R. So for making pizza, there is an R function called make pizza. That's a function. We call it function. Make pizza. Oh, command. Of course, there is no make pizza function in R, but you may think that any statistical analysis is like making pizza. So make a pizza. But it's good. A computer will not ask you, as the waiters do in the restaurant, in the good restaurants, how would you like this pizza to look like? You have to specify it by yourself at the very beginning. So let's say I want to have pizza on thin dough, and the rest is a specification for the specification given to this function is called function arguments. So dough, I want to have thin, dough equals thin, then comma. After comma comes another argument, sauce, I want to have tomato, and after comma comes another argument, main ingredient, I want to have it equal to mozzarella. And another comma, double cheese, no, I don't want it. I just want a regular cheese, that's okay. So I set it as false. There are arguments which are true or false sometimes, and the true, it's always written in capital letters. So false means don't do double cheese for me. And in this way, we're gonna ask for making any statistics. Like in the future, in a couple of slides, I'm gonna ask R, hey, make ANOVA for me. I want dependent variable to be this, independent variable to be this, and use these data for me. And that's it, boom. And you will have ANOVA results. So it's simple as it is when you think about talking in R. Being more realistic with R, for example, if I want to open the data, so I want to load the data into R, let's say that I have the data in a CSV file on my computer. I will say create the df object, which is abbreviation from data frame, and then assignment sign, create it. What I want to do, read CSV file. I will use this function. There are a couple of functions which is good to know by heart. You will not know all the functions in R. I think there is no single person in the world who knows all the functions in R language. That's why we use Google for helping us how to read a CSV file. For example, if you forget this function, read CSV, how to read CSV in R. If you Google that, probably you will find very quickly the answer. And then we have the arguments, what file we want to open. There's a file equals, and in quotation, we give feeds.csv. That's a name. So this is just general structure of any order we give to R, or any function we give we want to execute in R. Don't run this code yet, because you will get an error. We don't have feeds.csv file. It's just the general form of how we want to make it. So translating this into English is, I want an object df made by reading this CSV file called feeds.csv. That's a translation into English. So good so far?
Yes.
Thank you.
Okay, so move forward. Where are the functions? And when you download R, it has plenty of functions in it already. But R is built as a community language. So let's imagine that Miroslav has an idea for making some fancy statistics for tourism research. And he knows that he wants to make it very specific for tourism, for tourist research. So he can create a package of functions for this purpose. And he can call this package somehow, like a Miroslav package, submit to GAN, which is the society keeping R, and if they approve it, they will post it on their website. And there are plenty of such people working on libraries which are built for different purposes. Like, for example, there are several libraries for making running ANOVAs easy. There are several packages or libraries, this is the same, packages for making regression analysis easy, right? There are even some packages for making eye tracking analysis easier. And the authors of the packages, they put different functions into their packages. Uh, and of course, these functions has different parameters. Uh, what is what you need to do to use these functions, which are hidden in Miroslav package, you need to install the package first. First of all, you need to install the package as addition to your home computer. You can do it within R, and that's the only way to do it. I mean, the easiest way to do it, to install the packages within R. And if you have it installed, then you can load the packages to R session. And then you're going to be able to use all the functions which are there with, of course, parameters of these functions. What is super nice that all these packages are reviewed by the community, and they have all extended help and descriptions. What they do, why people created this package, what it is meant for, what kind of functions it contains, and who should use it. So this help and documentation is really extensive. So it's somehow exceptional for this R language. How to load, let's say that I have installed already a package called psych. Um, and someone created this package for psychologists. So if I have it installed, I type in a script, library, and the name of the package in brackets, psych. And I know that within this package, I found that there is a function called describe for descriptive statistics, which has a full list of arguments. Probably I'm not gonna need all these arguments uh, anytime I'm gonna use this function, but maybe sometimes just some of them. But pay attention here. This is what I found in the help of psych package. The describe function has all these arguments, and some arguments are already set as default. Like, for example, NARM remove uh, missing values is set by default to true. So if I want to use this argument as true, I don't have to do anything else. I just have to remember that it is set to true. Okay, don't go into details too much. Let's go further. Where you can find the description of these functions um, in the help tab. If you want to see what the function read CSV is doing, and you type here read CSV, and immediately it displays the whole help for this with description, what is it is meant for, how to use it, and what are the meaning of all arguments it has. RStudio is so nice to us that it knows that not all that will not remember the exact names of all the packages. So if I just have a slight memory that this function was starting with something like read, I know what was the rest of the name of this function. So I start typing read, and it helps me with the full list of functions available in this session to me, which starts with read. Okay, then I choose from the list read CSV, and it opens here. So RStudio is helping in this way a lot. How to install packages. And this is what what I will ask you to do for running the analysis we are going to talk about today, to install a couple of packages. Um, you can type a code to install packages, um, and the function to install packages is simple: install.packages. One very important reminder: R is a language which is case sensitive. So you cannot write install with capital letter. It has to be a small letter. It has to be exact name. And this is the point which for beginners causes sometimes a lot of frustration. Um, we have to be super exact here when we write a talk, when we talk to R, when we write a code. Exact in the names and also the each letters. If you make any typo here, the code will not execute. So pay attention to this. I keep saying because Isa was working as well on mindfulness. So I keep saying that one of the best mindfulness training is coding, is computer coding, so, because you have to be really focused on what you're doing. If you don't want to write the code for install packages, you can do it from the user interface in RStudio. You go to the tab packages, and you have the full list of packages which are installed on your computer. But if you click this install button here, the small prompt will show up and it's enough to type the name of the package you want to install. Again, it helps you with these names and it installs from official CRAN repository. And it's enough to check this install dependencies checkbox, click install and go. In our console, you will see the execution of your request. So the R session, it says installing packages, blah, blah, blah. It's not important to read it. It's important to just read at the end that the downloaded binary packages are somewhere and that they are installed, that there are no errors. That's it. So yeah, for example, library ggplot2 is for making beautiful plots. We're gonna use this library. We're gonna use this package a lot. When you install the package on your computer, it doesn't mean then that you can start using this immediately. The next step, you have to load this package and all its functions into the current R session. So you can load the package into current R session with the function library. You already know this function, library, and in brackets, you give the name of the package you want to load, or you can go to packages again and search the list you have of installed packages and check next to the name you want to load. Yeah, and you see in the console the execution actually of this function. The checking this button executes the function library ggplot2. Let's go next. Some libraries, don't be surprised, contain other useful packages. Such a great library is, example of such a great library is tidyverse. And that's a package you're gonna use a lot and you're gonna need for executing the code we are talking about today for sure. It contains packages like ggplot2 already and the full list of other packages which are super useful for manipulating the data and making a really nice graphs. So this library, this package tidyverse is meant to help you with manipulating your data and making nice graphs out of your statistical analysis. So I love this package. It's very, very useful. It's good to have it in your toolbox. So first code I'm gonna write in my R script is a load of library. Uh, why I put it in the R script? Because if I close the RStudio and then come back after some time to this, I don't want every time to remember which packages I was using and every time to load them into the current R session manually. So I put it in the R script, library tidyverse, and that's it in the brackets. And if I come back to this code and execute the line 2, it will load the tidyverse packages into the current R session. Please pay attention to line 1, which says there's a hashtag load useful packages. Useful is written by 1L, right? I did a typo here, but I'm quite safe because hashtag here in R is not a hashtag, is not a Twitter hashtag. Hashtag actually here means a comment. Comment is a part of the text, is a part of the code, which will be displayed in our console. However, it's not going to be executed. So hashtag, everything with what is after hashtag is not a code to be executed. So you can make typos there. Um, and and hashtags after hashtags are something like notes for yourself. I put a lot of notes to be to translate as well to myself what I want to do for the next code, for the next couple of lines of codes. And if you see my materials, which I sent yesterday, there are lots of hashtagged lines with some kind of a description what the next part of the code is doing. I hope it's readable. It is readable for me, so that's the only criterion I was using yesterday. Yeah, so with hashtag, the after hashtag, everything is not executed, just displayed. So let's move forward. We talk about the libraries. We know how to install libraries and how to load libraries into our session. Two different steps. Now let's talk about the data frames. And the first step when you do the statistical analysis, the first step before we run statistical tests is to prepare the data frame for the certain test you want to run. So let's say that we downloaded the data from real eye tracking platform or from other eye trackers. And you have this CSV file with fixations and saccades. But first of all, you need this data to be loaded into R. So you need to open this data in R and then manipulate probably then a bit before you run the statistical tests. So let's talk about opening data to R. Data are usually stored in the form of data frames. And a data frame is a quadratic table. When I was digging into the computer science a bit, I was surprised first that there are tables which are not quadratic but have more dimensions. Anyway, for us, table is table, has 2 dimensions, has columns and rows, and that's it. So it's a quadratic table, and you can think of this that rows and columns are numbered from 1 to infinity. So in columns, we store variables in data frames. In rows, we store observations. It does not have to be the person in a row, only the person, only one person in one row. It can be any type of observation level in rows. Like for example, let's imagine that you have data from one person only, and this person was performing some 2-minute task, and you collected several fixations from this person. So in columns, you will have variables, and in rows, you will have single fixations. As many rows you will have in a data frame, as many fixations the person performed. Let's try to talk, let's talk a bit more about the data frames and how to manipulate with the data frames. Here is some code for testing for you, for playing with data frames. First of all, making the variables, then at the end, putting them into one data frame. But very often we just load the data from the file. So let's switch to this part. When you load the data frame from the file, at the end, you have columns with the names of your variables, and you have rows with observations. Okay. If I load the data into data frame into R, in the R environment, you will see the data appearing and its name. Its name is, for me, is DF, is a default name I'm giving to data frames when I'm working with. And you have some information about this table. It has 10 observations and 3 variables, right? When you click on this small table button, the data frame is going to be displayed next to the R script. All right. Um, um, you can, what's really nice, that you can have as many data frames opened at once, as many you need. We're going to use it later on. Couple of very useful functions to play with data frames. And these functions I can strongly recommend to remember and try to remember later for use. We use it like every day doing statistics. Uh, First function class. If I put class and then in the brackets df, so this is my data frame, which is opened already, I will have the information about all the variables classes, or the classes of all variables. Variables can be of different classes. They can be numerical variables, they can be categorical variables, which is a string of characters often. They can be factors, right? Or they can be any different programming class. Function dim, means dimensions. So it gives you the dimensions of your, the size of your table. So it gives you the number of rows always as a first number, and the number of columns always as a second number. So when we think about the table, number of rows is always first, and number of columns is always second. Names df is the function for displaying names of all the variables which are already in our data frame. So example you have here, names df listed 3 variables, gender, x and y. Str means structure of your data frame. It gives you more detailed information about the classes of your variables, and also some examples of values which are stored in these variables. And a very nice function, head_df. If you work on a large data sets, and very often with the eye tracking studies, we have really large data sets. It takes a while to display it in the form of table, the whole data set, data frame. It's much quicker sometimes to look only at the first 6 rows, and it's enough for us to look at the first 6 rows. So the function head_df displays in our console first 6 rows of your data frame. These functions are really good to memorize. Class, dim, name, structure, head. Okay, so let's say that we loaded the data frame into our R session, and we can use variables from this data frame, call a specific variable from a specific data frame. You have at least two basic options to do it. Uh, First option, you give the name of your data frame, like here, df, and after dollar sign, you give the name of your variable. So for example, I want to display the values of gender in my data frame. I type in R console df dollar, so I refer to df data frame, then dollar gender, and it displays all the values of my gender variable. Or I can refer to variables as referring to the number of the column where it is stored. I will call it index. So let's say I will do it in this way. Let's say I have the data frame df, and when I want to refer to the index of column, I put the squared brackets, and the first I leave empty, then after because I want to display all the rows, then after comma, I say display the values of first column. First, in the data frame, rows are always first and columns are always second indexing. Um, so going a bit further, um, we talk about data frames, but we haven't talked about creating objects in R. Because reading data frame is something like creating an object, which is of the class data frame, and we're gonna use later for the analysis. So we create the object like we create lunch with the assignment sign, and we create it with the function, right? These objects are visible on this environment list for further use. We can have data objects, we can have values, we can have functions here, we can have plots here as well for further use. So whatever you create with this assignment sign with some specific function is gonna be stored temporarily in your environment. Remember that whenever you close the RStudio, you close R, everything from the environment disappears. Boom, this is like only working memory, which we have for now, for this session. If you want to remove an object from environment, use the function rm, which is remove. Okay, let's talk about some research, and let's move to the specific data. I have a data, I have borrowed the data for this lecture, for this workshop, from Anna Mazurowska, who is a student of mine. And she did a really nice eye tracking study with Real Eye platform entitled Climate Change Overlooked, the role of attitudes in visual attention to global warming. So the main hypothesis of Anna was that individuals with environmental concerns will be more likely to attend images depicting negative consequences of climate change than individuals without such concerns. Okay. Uh, she did a study on 48 psychology students, and that was two-stage study. In the first stage, the real eye tracking experiment was performed. In the second stage, participants were asked to fill out the new ecological paradigm scale called NEP. This is a measure of pro-ecological attitudes. We can call it sensitivity to climate change. And she wants to find out the relation between this sensitivity to climate change and the attention to negative pictures presenting uh, consequences of climate change. The eye tracking study was quite simple. After the instruction, there was a fixation point to uh, make all the participants starting looking at the main stimuli from the same point in space that was located in the middle. And immediately after fixation point, the stimuli with three pictures was displayed. Um, there were several of such slides with pictures which are positive, negative, and neutral. She tested beforehand, before the study, whether the pictures are positive, received as positive, negative, and neutral. So she's safe here at this point. And people were seeing several of such slides with these pictures randomized in the location. So they were randomly placed in these three locations, right? Um, And at the end, this new ecological paradigm scale is a scale of several questions to which you can strongly disagree, or statements to which you can strongly disagree or strongly agree. You see the example of two um, sentences, items of this scale on this slide. And this is the exemplary recording from real eye, how the person was looking at the trial, at the pictures. I don't know who that person was and what was his or her attitudes toward climate change, but we see that she explored uh, quickly um, all the pictures, focusing at last on the positive picture. So what Anna did in this study, she defined three areas of interest. Uh, that's neutral pictures, positive and negative pictures. What she did in the names of these areas of interest, she constructed the names in this way that she put the neutral, the valence of the picture first, and then underscore, and then the name what is presented on the picture. I'm not sure why she needed, but and why she complicated this in this way, but that's what she did. And we'll try to deal with this in data. So that's a negative, it's in Polish negative, and positive means positive. Okay. So that's a study we have, and that's the data Anna provided to us for this course. So to play with these data. So these are actually real data, as you may see. So let's try to play with these data first. First of all, I assume that what I did, I installed Tidyverse package on my computer, and I loaded it into the current R session. So I'm going to use functions from Tidyverse package, which I called an excellent tool for manipulating with the data. When I want to first read the data, so I typed in the code. Let's create the df object for me. Let's create it with the assign sign here. And I started to type read, because I know that read is something like read the file, read the data, and it helps me with automatically, RStudio helps me with these different functions it has already. So I will choose the function read underline CSV from Tidyverse package. It seems to be quicker than read.csv. I'm going to use it. And there's a more extensive help what the function is doing. So I choose this one, and then I type further. I say in the brackets, file, which file I want to use, which file I want to read, equals, and oh, remember I have it in the data subfolder. So I type in data, then slash, and if I press tab on my keyboard, it helps me with what kind of files I have in this data subfolder. So RStudio is actually reading the files beforehand, and then it displays in the help. So I don't have to remember exact names. So I can choose from this list reali.csv. I know that the data from eye tracking experiment are stored in this reali CSV file. Then I click enter and I execute the code. What does it mean I execute the code? So I place my cursor in the script on this line, and I can click a small button which is above uh, in the upper menu, which is called run. Or I can use a shortcut. On Mac, it's command enter or command return, whatever you like to call it. On Windows, it's control enter. And then this line, this particular lines goes to the console, and it is executed. The display then console displays what this function is doing. It's reading this file realize CSV, and this function is displaying actually what are the names of the variables, what kind of variables it has read, what are the classes of these variables. So double means numeric. So I see that the ID is numeric. I have some character variables here, AOI ID, AOI name, size percentage, fixation total count, fixation average duration of milliseconds, fixation time to first fixation milliseconds. So some names of these variables are self-explained, some are not. Let's look closer to these variables. When I execute this first line, I have in the environment, I can check that in the environment, I have my data frame opened, and it has, wow, more than 6,000 observations, more than 6,000 rows and 10 variables. Okay, click on this small table here, and you will see it will open next to the script. It will open the table for you. So you see what's here, what are the values. So AOI name is actually, we see the names which we're giving to our AOIs. AOI ID is somehow a strange variable. I think it is created automatically by Real Eye platform to keep the ID for technical reasons, to keep the ID of different AOIs. And actually, probably this AOI ID variable is not needed for us for further proceeding with the data. We can check how much percentage of the entire screen, entire picture was actually occupied by each AOI. What is quite nice that all the AOIs listed here, they take a similar percentage of space, around 13 percentage of space. So it means that they are somehow standardized, and at least we may say prior to the analysis that there's the same chance probability for all participants to to gaze at each AOI. If every participant would gaze at different pictures randomly, completely, so there's the same amount of chance to gaze at each AOI. Then we have total number of counts of fixations in each AOI. We see that the first person looking at negative AOI exhibited 7 fixations. The same person looking at neutral AOI exhibited 7 fixations. And when looking at positive, the same person looking at positive exhibited 1 fixation. Then we look at 3 rows of this next person for negative 11, for neutral 0, for positive 2 fixations. All right, let's go next. I don't like actually these AOI names, and we need to do something with this. Sometimes you have something in mind when you create the AOI's names, or you create the variable values, but then it appears that you don't need such a detailed names. Why the unique values of AOI name variable are listed here, but actually what we want to check um, in this study is to check how many fixations were and how many attention was put to negative, neutral, and positive pictures. So what we want to change here, we want to get rid of this. We want to change every name to be only negative, neutral, or positive, right? Of course, you can do it in Excel or in CSV file directly by hand to change negative, underline project to negative, negative only neutral, positive to neutral, and so on. But we can do it in R in a much quicker way. So let me introduce you a concept of pipeline here, and we'll use this function separate for the purpose we want to achieve here. So we have already loaded the DF folder. I'm sorry, DF data frame. So I want to somehow manipulate with this data frame, but I don't want to change its name, right? So let's say that we can do it in this way. That I will create a new data. I will create an object DF. So I will overwrite it, and that's created with DF. And then we use this special assign, which means the pipeline. So it means the pipeline is exactly what it means. So it means take this part of the code, take this line of the code, and then with this object, do whatever is written in the next line. And after doing this, we can make another pipeline and write another line to do the next thing with these objects, right? Just like step by step doing something with one data frame. Somehow useful. This sign to type can be complicated. However, RStudio has a shortcut for this. This is a Control-Shift-M keys. When you press them immediately, it will give you this pipeline sign where the cursor is. So actually, to change all these names, it is enough to separate these names into different columns by this underline here. So in one column, we'll have values only negative, neutral, and positive, because that's going to be left. And in the right, in the second column, we'll have all these values which are after underline. right? So we're gonna use the function separate from tidyverse package to do it. So with df after pipeline, I write separate, open the brackets, and then what I want to separate, I want to use the variable AOI name. I'm gonna use this variable. After comma, what I want to do, what the separator is. Again, I looked at help, so it helped me to know what arguments I need to put here. So the sep is equals to underline, so it will separate with these. And after comma, into what? Into two different variables, into two different columns, AOI type and picture. Let's see means concatenate with two different columns.
Krzysztof, can I have a question?
Sure.
Following what you're doing, and I got an error, and I can post it to the chat. It does not recognize the percentage wherever you've got it.
Let me check this. Okay, it's simple. You have to first, I'm typing on chat. You have to first load the tidyverse library into your R session. Because this pipeline sign is created within this tidyverse library. I'm pretty sure that that will solve your error. If you have any kind of such an error, like I cannot find function, blah, 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 it means that you did not load the library which contains this function, which you intend to use, right? So come back and load the library. It works perfectly. Thank you for the question. Any other questions? Okay, it's good to know that at least someone is doing what we talk about right now. Let me try to close the chat. I will move forward. Okay, we have more pipelines here.
Sorry,
Okay.
Krish. Sorry,
Yeah.
Krish. You sent it via email, the data sets we will be using. Okay. Okay, thanks.
It was yesterday.
It was yesterday. Okay, thanks.
Yeah, if anyone did not receive it, I can resend the email. That's fine.
Maybe, Krish, somebody is asking in the chat, maybe just to give him a little more time to type the command line and to test it.
Yes, sure. Sure, we can even have a short break in a few slides if you want to test something, okay? But let me introduce some two other very important functions here from tidyverse to manipulate the with your data. Now, very often you want to select some variables, or you want to get rid of some variables. And sometimes you want to get rid of some subjects or some rows from your data. To select the variables, we use the function which is called select. And I here have an example when I want to get rid from my data variable which is called nodes. I want to get rid this variable AOI ID, which already we have looked at, and we've seen it has some meaningless information for us. And we want to get rid this newly created variable called picture. How I get rid, I do select and I say minus nodes. Minus means remove this variable, remove this column. Then I have the pipeline again, and I know from Anna that I need to filter out 4 participants because she figured out somehow that these 4 participants were not following the instruction, and their data are not really good. And the participants' subjects ID are stored in the variable ID. So I say filter ID not equal to, she provided me with the names of these, with the codes, IDs of these subjects. Not equal to this one. Not equals is the exclamation mark, and equal, just followed immediately. And ID not equal to this one, and ID not equal to this one, and ID not equal to this one. Pay attention, this is logical not equal. Exclamation mark equals, it's not equal. So we want to get rid of any observation, any data we have from these 4 guys. It will filter out their whole data. And when I type names df at the end, I see that I have ID, AOI size in percentage, fixation average duration, fixation average total time, AOI type, which is negative, positive, and neutral, fixation total count, time to first fixation, and first fixation duration. These are the nice variables we're gonna use for the analysis. Okay, one last thing before the short break, and it's very often useful when you have the when you collect the eye tracking data. Quite often you have a missing values inside your data frame because the eye tracker stopped working. There's always a different reason for why you have a missing values. All missing values in R are annotated as NA. NA means missing value. And actually, any statistical tests don't like or doesn't like missing values. And always when you see the missing values, you should think about why you have it. Sometimes it really, there is a reason for this. Sometimes you want to get, there's a reason which means that you should change a bit your data, or you should change something in your procedure. And sometimes you have the conclusion that you can just get rid of all the participants who has missing values. There are different solutions. In this case, I noticed missing values as well in the data frame. And I realized after some consideration that these NAs means that the participant, the certain participant, did not look at the certain AOI. So Real Eye platform put the NA in this record. Instead of putting 0, it puts NA. So for example, like me looking at these 3 pictures, I did not look at the one picture, a positive picture. So I will have an A in the number of fixations on this AOI. I should have 0, but it gives me an A. So let's deal with this. I can replace all NAs, and I check manually that it's the same pattern is there for all participants. So I can replace NAs with zeros, and it's simple function, replace NA. Again, you have a pipeline here. I cut the code into small chunks, but actually, if you work with your code, you can build the whole pipeline pretty long at once. Anyway, uh, again, pipeline replace underline NA is a function I want to use. And then in the brackets, I give a list of variables in which I want to change NA values. So I give the name of this variable. I want to change the NA values into zeros. After comma, next variable, I want to change the values into zeros. And in every variable, I want to total time, average total time, average duration, I want to change NAs to zeros as well. Because it makes sense in this case. In the other cases, it might be something different. So at the end, we have these, we have very nice data frame with eye tracking data. But as I told you, there was also the second step with the questionnaire of sensitivity to climate change. And this questionnaire was performed in the with the separate questionnaire software. So we have we have two different data files actually. We have a data file from eye tracking study, and we have a data file from the questionnaires. These are stored in these questionnaires. Answers are stored in the file called qualtrics.csv. So what I want to do, I want to open a new data frame. I will call it DQ data questionnaire. I'm going to use the same function with CSV file Qualtrics. I see that there are a couple of questions and ID. This ID is important. This is a subject ID. And I ask Anna to be sure that these ID are the same as the ID in eye tracking in real eye data, and they are. So having these two data frames, we want to join them together by this subject ID. To join two data frames by subject ID, even though that these subjects ID, these two data frames has really different length. Look at this. DF has more than 6,000 observations, and DQ has 48 observations. Because in the DQ, in the questionnaire data, one row is one person. So in one row, I presented the answers of one person. Okay. In eye tracking data frame, number of rows is number of people multiplied by number of areas of interest. Even though we can combine these two data frames, we can join these two data frames or merge. We have different names for this. Let's join them by subject ID. To join these two data frames, I'm going to create a new data frame called D, and I'm going to use the function inner join. Then I give the names of data frames I want to join. First, I give DF, that's a main data frame, and DQ as the second questionnaire. I want to join them by the variable which is called ID. Even if I forget to do it, and that's the only variable which has the same name and values in both data sets, it will do it automatically by this variable. When you run this code, it will create a new data set with much lower number of observations than the original eye tracking file, but with the higher number of variables. We have, instead of 8, we have 10 variables. or maybe even more if you have more. All right, and I think this is the almost last slide before a short break. And if we have combined these data frames together, we need to calculate the metrics for sensitivity to climate change. And it should be just a sum of all the answers people gave to questions to the SNAP questionnaire. So I add all the answers, and this is one number of sensitivity to climate change. I will call this new, so I want to create a new variable, which is going to be called NAP, and it's going to be one indicator of participant sensitivity to climate change. So let's do it with the first row. I will mutate my data frame. I want to create a new variable NAP, which equals row sums, because I want the sum of one row of each row. And then I select all what I want to sum. I want to sum the values in this selected variables, which starts with Q. It's a bit more complicated. We have function, in function, and in function. But it works beautifully. So you can nest your functions. So if we have this NAP column with a numerical indicator of your sensitivity, of our participant sensitivity to climate change, then for analysis with ANOVA, we would like to have as well the factor which will split our group into two of people with low and high sensitivity to climate change. Very often we use the what we call the median split. So we look for the middle value in the data, and everyone who is below this value, that's median, everyone who is below this value is going to be labeled as someone with low sensitivity, and everyone who is above this value is going to be labeled as a person with high sensitivity. For cutting the NAP variable into two, I will use function cut NAP into two. That means two. If you want to cut it into three groups, of course you can do it, but then the labels you should provide three. Median split is only for two. That's it. And super important or somehow important here. We have AOI type. We have neutral, negative, and positive, right? So let's think about these three values. Positive, neutral, negative, and positive. Which one is the basic value? If we think about it like about the, I don't know, hierarchy, which one should be the base? I think neutral. Am I right? I hope you agree. And then to neutral, I would compare how many fixations were in negative or positive to neutral. Neutral should be somehow the reference point for us. So it's going to be super useful in regression analysis later on. So to make the neutral value as a reference point for us, we need to change the type of AOI variable into factor. And this is this line. I change, mutate means change. I change AOI type to factor AOI type. So I factorize AOI type. And then I change in AOI times, I re-level this variable, and I set reference point as neutral. I want to do it deliberately. Typically, I want to have neutral as a reference point. If I would not do it, R would treat negative as a reference point. Why? Because with these three values, negative is first alphabetically. Then at the end, I want to get rid of all the variables with starting with Q because these are raw data from the questionnaire. I don't need them anymore. I already use them to calculate the NAP and NAP split factors, which I'm going to use for the analysis. And super last slide, let's save our data, which are combined and already mutated for the analysis into the to hard drive. I can use the function write CSV to write the in the same format. I write CSV what? The object D, which is actually our mutated data file, into the file which is called all data CSV. Or I can save it in a R data format. I will use the function for that save. And I will use the extension RDA or R data. Why use RDA or R data instead of CSV? If you work with R, it first of all contains less space on your computer. Even here, you can compare this CSV to RDA. RDA is 5 times bigger than CSV is five times bigger than RDA. And with the much larger data sets, this difference can be substantial. And as well, it's RDA it keeps as well all the names and types of variables which already were defined before. So RDA is much more useful when you work with when you want to continue working with R. Okay, guys. What would you say about 5 minutes break?
Sure. Stretch our legs.
Stretch legs, stretch stretch brain. I'm gonna check the chat because I'm not actually, I'm sorry, following the chat.
Yeah, I think nothing's going on in the chat. Everything's fine. Yes, Krejtz just send the slides. We can send them again, perhaps if somebody just joined in, they don't see the history.
You have PDF file, yeah, in the
Yeah,
chat.
I'm sending it again. So you have it and the recording will be available. So no worries. So
quick break.
5 minutes, yeah.
5 minutes maximum, yeah. We're gonna be back soon. Okay, this meeting is being recorded. Hello again. You may think now, I just want a pizza. And where is this pizza? We are doing all this preparation for making pizza, but where is the pizza? I need a pizza. The lunch is approaching. So yes, let's finally order the pizza. From the analytical perspective or experience, I must tell you that the preparation of the data for file before making analysis usually takes really long time. One of my collaborators, Andrew, is he tends to send me a new data sets and asking for some new analysis, saying, it's going to be super quick for you. You will just run the code for some ANOVA and regression, and we'll have nice statistics. It will take you maximum 2 hours, and it usually takes me 2 weeks to prepare the data before I can run the ANOVA actually for 2 hours or so. So preparing the data is always a big step. So that's why I spend a lot of time on this as well here. But finally, let's have a pizza, and we'll start with the somehow advanced mixed design analysis of variance with two variables. One variable is going to be one variable is going to be between subject variable is going to be attitudes toward the climate change or sensitivity to climate change, low and high, as we created already this variable. And the other is going to be AOI type or AOI valence, which is going to be within subject variable. Okay, just to remind you that the analysis of variance called ANOVA is a generalized t-test. It allows to compare the averages, the means among 3 and more groups or 3 and more conditions. The null hypothesis for ANOVA is that the several populations or several conditions have the same mean, and the alternative hypothesis is that at least one mean is different. So that's a basics of ANOVA. We're going to use 3 useful libraries here. Tidyverse, you know already. Affix is a new variable for you probably. In the affix is built to make ANOVA run easier. And I love this package and I love the functions, how they are created. I really, that's why I share with you how to use affix as well. EM means is another library which is super useful to run post hoc tests after obtaining ANOVA results. EM means stands for estimated means, estimated means. Okay, now let's say that we closed our R session and we see the next day to run the statistic because we got tired with data preparations. So we first load the data into our session, and for reading our data format, I'm going to use the function load, which is a generic R function. And if you just type load and give the name of the file you want to read, it will load already the name of your data frame as it was saved. It was saved D. It will load all the variables and the classes of these variables. So everything is ready to run the analysis. So we have a data frame called D. Then I load the function, the library affix. As I said, it's pretty convenient. It provides pretty convenient functions for analyzing with ANOVA. And the general form for using these functions is as follows. For example, we can use the function AOV, which stands for ANOVA, underline EZ, probably ANOVA easy, EOV underline EZ, and we have a couple of parameters we can define here. So EOV easy is make pizza. We have a couple of parameters. ID, we have to give the subject ID variable here in quotation marks. We have to provide data frame name. DV is dependent variable. We give the name of the between subject factor. In our case, it's going to be sensitivity to climate change, and within subject factor. It's our case, it's going to be AOI type. With this same function, you can run as well covariate analysis, covariance analysis, if you provide the covariate variable. If you don't provide, it will just run ANOVA. And by default, it's set to run the type 3 ANOVA, which is very useful for social and humanities studies, where the experimental design is not perfectly, and experimental data are not perfectly balanced. I will not into details of this, it's too much details. So we have 2 hypotheses to test. First, now I translate the general hypothesis of this study into analytical hypothesis. In general, negative and positive pictures should evoke longer fixation durations than neutral ones, because positive and negative, they have emotional valence in it, and it will evoke longer cognitive processing of these pictures, probably. I think it makes sense to me as a psychologist. I hope it makes sense to you in general. But I think that we can also say or state the hypothesis that these differences are going to be changed, moderated by sensitivity to climate change. So probably that that pattern of results, as in the first hypothesis stated, is going to be visible only among people with high sensitivity to climate change. It's not going to be probably true among those who don't care about climate change. So the second hypothesis is actually the hypothesis about the interaction effect, and the hypothesis about the moderation effect of the results. So how to run this and how to order pizza. I will create the object feed, which will store all the results of my analysis. Then I'm going to use these results to display them, to play with post hoc analysis. That's good to have it stored. So I will make this feed object, and I use the function EOVEZ as data. I say use data D without quotation. Pay attention here, because D is an object already. But within this object, I'm going to use ID as subject ID variable. I will use AOI fixation average duration MS as dependent variable. As a within factor, I'm going to use AOI type, as we said before. And as a between subject factor, I'm going to use NEP split. That's a factor we created before the break. Okay. If you run this code, the R console will say nothing to you. It will just say, boom. It means I did it without errors. But then you can type print feed. Print is give me the result. Print on the screen what you have. Print feed. It will display the basic table of results from ANOVA. What we see from this table is that we have three effects. We have two main effects of NEP split factor and AOI type factor, and we have the interaction effect of NEP and AOI type.
You have a question in the chat. Not sure if you want to address it now. Can you put more than one within subject variable in this function?
Yes, you can. Yes, of course you can. Just remind a couple of slides ago, we used the C function as concatenate. So if I would like to have more within subject factors here, I would say C, open the brackets, and put all the names of all the variables which I want to use as within subjects after commas. The same applies to between. Of course, dependent variable can be only one. Boom. I think that answers the questions.
Excellent, thanks.
Let's go to the results. Let's look at F statistics, which is the statistics of ANOVA. And for NEP effect, it says it is lower than 1. And when I look at p-value is higher than 0.05. Both of these says this effect is not statistically significant. So there are no differences between people, in general, people with high and low sensitivity to climate change in their fixation durations. That's good, I guess. But let's look at this AOI type. We had the hypothesis about the AOI type. And this F is pretty big. This p-value, which indicates the statistical significance, is lower than 0.001 even. So it's below the threshold of 0.005. So this effect is significant. Or even mark it with 3 stars here, saying that this effect is highly significant. So we may say that the hypothesis 1 is confirmed. At least one of the AOI types, positive, negative, or neutral, got longer or shorter, significantly longer or shorter fixations. We will have to split this effect with post hoc analysis, with more detailed analysis to check whether really this hypothesis is confirmed or not. We'll see it just in a moment. Look at the interaction effect. It's marked with cross. It means, and we look at the p-value, it's slightly above 0.05 threshold, but it's below 0.1. So we might say that this effect is not statistically significant, but it is marginally significant. Oh, maybe if we would have more participants in the study, maybe if we would change the bit stimuli, we would get significant results. So it gives us the hope that there is something in these data which say that probably this interaction is true. We'll look closer in this interaction, okay, in a moment. First, let's look at this main effect of AOI type. So first of all, let's estimate means for fixation duration while looking at different types of AOIs. I'm going to use the function em_means for that. In this function, I put the object fit, which is the results of my ANOVA. Just from these results, from this model, I'm going to estimating the means. And then after comma, I give the tilde sign, which is easy to type on Macs, and it's harder to type on Windows computers, but you can do it. And there's empty space, tilde sign, and I put the name without any quotations of this effect I want to look at. This is AOI type variable, our factor. Again, I created the EM object because I'm gonna use this table later on. So we have this, define this, this object. When I print the print EM object, I receive such a table which says that neutral, you see neutral we set as reference. So that's why it's displayed as first here. That neutral pictures on average, their fixation duration was 127 milliseconds. Negative AOIs got on average 1:1 fixation duration, and positive fixation on positive pictures fixation duration was 148. So even looking at these means we say we are closer to confirm the first hypothesis. Negative and positive pictures got pretty similar average fixation duration, higher than neutral pictures. Let's compare where the differences are. So I'm going to run now the post hoc analysis, which are called sometimes pairwise comparisons. So I want to compare each of these values with the others. So I want to run 3 comparisons. And I'm going to use for that the function pairs. First, em, I put this table into this function. And it gives me the contrast, the comparisons. Neutral comparing to negative, the difference is minus 1445. And this difference with t-test, because it runs like 3 t-tests, this t-test is significant. So the difference between negative and neutral is significant. The difference between neutral and positive, I look at the p-value, is significant as well. But the difference between negative and positive value is not significant at all. Now I can fully say that yes, first hypothesis was confirmed. Why I use pairwise comparisons with these functions pairs, not running 3 t-tests by hand, because with this function, it adjusts the results with a special correction. By default, it uses Takei method for the correction for number of comparisons. The more comparisons you do, the more tests you do, the more probable that you will get the significant result by chance. So it takes it into account, and we say in the paper that we did the pairwise comparisons with Takei method correction for comparing the means, and it gives us, we are more certain about these results. Let's plot it. So we want to see these results. I'm going to use the function EMMIP from means package. And again, I put the results of ANOVA here as a first argument, our feed. And after comma with tilde, I want to see the results of the main effect of AOI type. When you execute such a line, you will receive such a graph in your graph tab in RStudio. And it says that linear predictions are here. This is our dependent variable, so it's average fixation duration. It's lowest for neutral pictures and higher for negative, and even higher for positive. But we know that these two means, these two values are not significantly different. But this one is different from the others. All right. Actually, this graph is good to quickly look at the results, but I don't like it as a graph for publication. But anyway, let's go. We'll talk about it a bit later. Now let's look at the interaction effect. If I want to have the table of estimated means for the interaction effect, I'm going to use the same structure. I'm going to create an object EM, use the function EMMeans, give the results of ANOVA, and after tilde, I give the interaction AOI type, and there is a colon, NEP split. So I want display or estimate means for this interaction. Okay. And when you print EM, such defined EM, you will have this bigger table saying that average fixation duration while looking at neutral pictures for people with low NEP values was this 134, for negative 138, and for positive 150. For people sensitive to climate change, looking at neutral is 119, 100 for negative 144, and 147. It's not, now let's check which of these averages are significantly different. So we're gonna run 2 pairwise comparisons here. We need to run 2 pairwise comparisons. First, we're gonna split this table by NEP values. And then, so we want to compare separately for low NEP people, their means for neutral, negative, and positive AOIs, and high NEP people, neutral, negative, positive values. So first we want to separate it by net, and the other pairwise comparisons we can do by AOI type. So let's look how it looks like. First, we do pairs EM by NEP split. Okay. So you have such when you print, when it's automatically printed on in console, and you see the NEP split low for people with low values of NEP. The differences, look at this. The difference between neutral and negative is not significant. The difference between neutral and positive is not significant, is marginally significant, but it is, yeah, still not. And difference between negative and positive is not significant. But look what happens here for people with high sensitive to climate change. The difference between negative and neutral is significant, between the same as positive and neutral, but between positive and negative is not significant. So wow, we got it. I think we confirmed the hypothesis too, meaning that people which are highly sensitive to to climate change, they pay more attention to negative and positive pictures presenting the climate, while the neutral pictures, while people who don't care about the climate change, they don't care about whether the picture is positive, negative, or neutral as well. That's what we see here. If you would like to compare it in a different way by split it by AOI type, it gives you such a table. So you have difference between average fixation duration between people with low and high NEP, while looking at neutral pictures, not significant. While there's difference while looking at negative pictures, not significant, and there's difference while looking for positive pictures, not significant. Actually, our hypothesis was referring only to this table, so it was enough to run this table, but I did it in 2 ways, just to give you the example how you can use it in different ways for your hypothesis. And when I plot this interaction, simply I will plot this interaction with EMIP function again. I put the results of the analysis here, and I put the interaction term here. I will put NEP split factor before tilde sign and AOI type after tilde sign. This short line gives me such a beautiful picture, such a beautiful graph of my results. I see that for people, and I know from pairwise comparison that these differences, this means for red line, so people not caring about climate change is not significant, but these two, positive and negative, for green line are different than looking at neutral. So I see the interaction here, which is printed already. Still, I would say that this graph is not ready for publication. I would like to make it nicer. First of all, I don't want such a graph to be linear, but rather bar graph, because its linear graph suggests that there are some values between neutral and negative pictures, but they're not. So first of all, then I need the error bars presenting confidence intervals around means. I would like to have all the axis of this graph labeled correctly. So I'm going to do it in a bit more complicated way to prepare a nice graph for publication. And I'm going to use the ggplot function for that. It looks a bit complicated here, so don't type it right now. You have this code in the materials, so you can play with this later on. Let me just quickly explain you the logic behind this code. So first of all, what we're gonna print in this graph, we're gonna print actually this table with estimated means. We have created already, but we need to change the type of this table, and that's for technical reasons only. We're gonna change this the class of this table with function summary. So I create a new object tab, summary EM. EM is my table. When I print tab, it gives me very similar output as just print EM, but it's a different type, so better suitable for use with ggplot. Then I create a new object, which is a new plot. If you don't create an object and run the rest of the code, the plot is going to be displayed automatically on in the graphs, in the plots tab. So with a ggplot, I create and the ggplot works in this way. It's similar to pipeline, that with each line, you give a new layer to your graph. So first, I say that I create the general aesthetics of this graph. So I'm going to use the tab as data for the graph. On X, I'm going to put AOI type. On Y, I'm going to put this EM mean values. And I'm going to use NEP split column for different colors of graphs, of bars. Then I give the pipeline sign. Pipeline sign for ggplot is plus. That's an exception in this language. And then I add the layer that I want the geometry of bars. So I want to have bars, columns, instead of lines. And I want on bars, over bars, I want to print error bars. Error bars means error bars for confidence interval. And I set minimum of X as lower confidence interval, lower confidence limit, which is here. And maximum X is upper confidence limit, which is here. Then I customize the Y-axis. I want to give it a new name. So I scale Y continuously, and I give a name as average fixation duration. That's the name I type by hand, which is in milliseconds. Then I want to manipulate the name of the X of the horizontal line. And this is discrete values line. So I give a name AOI type, and I label it as neutral, negative, and positive. And then I want to label as well this NEP split column, as name it as NEP. And the values, I give colors. And this is the definitions of colors I have taken from internet. You can put the code of the color you want to use. This is a HTML color, HTML code, but you can type as well in English, red and blue, and it's gonna do red and blue. I use these colors because these colors are friendly for colorblind people. So when they read my papers, I would like to make the papers more accessible for them. So that's why these colors I'm used to use. And then at the end, I can set the whole theme, the whole feel of or aesthetics of your graph with some general theme. There are several general themes. I use theme minimal. If you Google for ggplot themes, you will find out several of them with examples how they look like. So the theme I set as minimal. This is how I look, how I like it to look, and that's the result of this code. So that's a graph which I would use for the publication. So this orange depicts the highly sensitive people to climate change, and gray people low on NEP. So this neutral is significantly different than this one, and neutral is significantly different than this one, while gray bars, even this error bars indicates that there is no significant difference between gray bars in here. When you want to save the plot, you can, when it's displayed in your RStudio environment, you can click save or export plot, and you can choose save it in a different formats, or you can choose copy to the clipboard and then copy to the presentation. And that's actually what I was doing when I was preparing this presentation. Or if you love coding, you can save the graph with ggsave function. So you print it first, then you type ggsave what you want to plot and give the file name and where you want to store it and in what format. Let's say JPEG. I really recommend, instead of using JPEGs or PNG files, I really recommend of using PDFs, as PDFs are vector graphics, which usually keeps the quality despite what you're doing with the size of the graphs. Some journals require TIFF format of graphs. You can save it as TIFF as well, as you can see it. And dev off function means close the graph, device off, close the graph. Let me check the schedule for today. I think we are approaching the end of.
Yeah, we have 4 minutes left. Yeah.
Yeah, 4 minutes left. You have a couple of more slides there in the presentation. If you want to check the other dependent variable like fixation total count, and check the hypothesis, whether people look at how many fixations they did on different AOIs. We see that here we don't have the interaction effect. We have only AOI type effect. And the graph for that is would look like something like this, that the neutral pictures got less fixations than negative and positive in general, and despite what the sensitivity to climate change was. Yep, I said it again. Linear regressions. I'm sorry, linear regression. We will have to leave you for a better future. I'm happy to take some questions if you have any. If you still are with me.
There's still 72 people at least logged in.
Okay. It doesn't mean that I didn't put everyone in sleep. I can easily do it. So linear regression, you can. I hope you can follow the logic of what to do with linear regression with the code you have and slides. I was trying to beat these slides self-explanatory. For example, here, how to define the linear regression model as step by step, where we put dependent variables, where we put independent variables, and interaction term, and why we do it, and what we do when we have the mixed design and we want to run a regression model. I really recommend to go through these slides and the code because at the end you have something what is somehow awarding. These beautiful graphs. Do you still see my screen?
Yes, yes, we see.
perfectly. You have these beautiful graphs which somehow rewarding, at least for me, or even more beautiful graphs with something like this, with confidence intervals around it. So what we have here with this regression and follow-up simple slopes analysis is that we have different types of AOI, neutral, negative, and positive. And here on the y-axis is the net values, not divided by median, just values as they were for each participant. Okay, so and what we see here that the more sensitive to climate change you are, the more attention you pay to, this is fixation count, the more attention you pay to negative stimuli. And the less attention you pay to neutral stimuli. And for positive stimuli, the line is almost flat, so it doesn't care what kind of attitude you have. It does not predict your number of fixations. And that's really promising. I mean, this is like a new, it gives you maybe a more precise way of interpreting the data, meaning that the more sensitive to climate change you are, the more attention you put on to negative pictures, to negative examples of climate change. And less you care about neutral images which were shown to you as a participant of this study. Right. How to obtain this graph and this interpretation? You have it on slides. I'm sorry I did not manage to talk about them, but I'm gonna be happy to take questions and explain it if you want during the break or any time during this this call. I stop here.
Yes, thank